Hi, and welcome to Codex. Our speaker today is Tom Needham, who's an assistant professor at Florida State University. Professor Needham is known for using ideas from geometry to solve problems in data science and frame theory. Today, he will talk about fusion frames. Take it away, Tom.
All right, thank you, Emily. Thanks to all the organizers for the invitation. Thanks to everyone in the audience. Yeah, so today I'll talk about symplectic geometry and some applications to fusion frames. This is part of a long-term project with Clayton Shonkwiler from Colorado State. Basically, the idea is to do frame theory type stuff, but to use kind of weird ideas from differential geometry to try to get a different perspective on it. So we'll be using mostly symplectic geometry here. Okay, so let me tell you what I think a frame is, or to kind of set the notation for what frames are to me. So to me, a frame for the rest of this talk is going to be always in finite dimensional complex vector space, and let's just say it's CD with its standard inner product. And so I think of a frame as a spanning collection of n vectors where n is bigger than d. Okay, I guess spanning kind of tells me that it needs to be at least d. So then I'm going to organize the vectors by ordering them and kind of just putting them in as the columns of the matrix. So to me, a frame is really just a matrix in d by n dimensional space, which has full rank. Okay. Okay, and then so fine, that's a little boring, and typically what people care about are kind of structured frames. So to describe that, I'll introduce a few operators that are associated to a frame and maybe give a little bit of context about why you care about frames. So given such a matrix, we have an analysis operator, which is just conjugate transpose of the frame matrix. And the way we're supposed to think of that is we take a vector in CD and we think of this as like the signal space. So I have a signal and I take a bunch of measurements of that signal by taking inner products with my frame vectors. Okay, so if I organize all of those coefficients into a vector, that's the same thing as kind of hitting the signal vector with F star. Right, so I think of the analysis operator as going kind of from signal space to measurement space. On the other hand, we can, of course, go the other way. So going from measurements to signals, you can think of that as just basically the matrix F. So here I'm given a vector of coefficients, which I think of as coming from some measurements of a signal. Then I can take those as coefficients in this linear combination. That amounts to doing F times W. Then I reconstruct something in signal space. Okay, so of course, you need to go forwards and backwards, and you need to take measurements, and then you need to reconstruct signals. So doing that forward and backward move is corresponds to hitting something with the frame operator. Okay, so that's just the composition of, I have a signal vector, take a measurement, and then reconstruct something in signal space from that measurement. Now here's where kind of structured frames come into play. So a property that people like for frames is that, say, the frame operator is a multiple of the identity matrix. So then the process of taking a measurement and reconstructing is very interpretable. You reconstruct your original signal up to a scale. Usually people just say multiple of, I'm pinning this down as n over d because that's kind of a convenient normalization. And another way to say that is that the spectrum of the frame operator is constant. Okay, and that's kind of a useful way to characterize this for what we're going to do later. Right, then of course I can do this composition in the other direction, so I can kind of think of this as measurement to signal, then signal to measurement. Then I get what's called the Gram matrix. Okay, so that's just F star F. And then another type of structure that people like to put on frames is to say, well, all the measurement vectors are the same norm, say they're all unit norm. And this corresponds to saying, like, I kind of want all my measurements to have the same power, say. Another way to say that is that the diagonal of the Gram matrix, let's see, the Gram matrix really is just the matrix of all the inner products of the frame vectors. Okay, so then the diagonal is just the squared norms of all the frame vectors. So saying that a frame is unit norm is saying that I'm specifying the diagonal of the Gram matrix, say. Okay, so then now we're gonna kind of consider interesting collections of frames where I take frames and then I impose these kind of prescribed either like spectral properties or norm properties. And so we'll also use this as set notation. Okay, so my first collection of frames is just like all the frames. So I'll use script F super dn to be the frames in C d by n. And really that's just like all the full rank stuff. Okay, so that's an open condition. So this is an open subset of this vector space, or if I want to be a little bit more geometry-ish, it's like an open submanifold, which is really just means open subset in this case. But as I start imposing different kind of prescribed data on my frames, I start to get more interesting collections. And by interesting, I mean the kind of geometry of the collection becomes more complicated. So first I can prescribe a spectrum. So the example that we had before is we would say prescribe that the spectrum of a frame is constant, which is to say that its frame operator is the identity matrix or a multiple of it. I could generalize that and say, okay, what if I just allow arbitrary prescribed spectra? So I'll use capital lambda to stand for a spectrum type thing. I'm not sure that the ordering matters so much, but I'll order these in decreasing order. And since it's full rank, I'm going to assume that these are all strictly positive. And then I can say, all right, so let's FDN, I'll put a subscript lambda to indicate that I want to specify the spectrum of the frame operator of all my frames in this set. Okay, so this already becomes kind of an interesting object. It's a manifold whose quotient is diffeomorphic to a flag manifold. Okay, to pin that down a little more down to earth, if I think about the space of tight frames where I'm prescribing, say, a constant spectrum, then that is diffeomorphic to a Stiefel manifold. Okay, so the space of frames, N, where my spectrum is constant. This is frames in T by N, such that the spectrum of, or let me say it more quickly as really the frame operator is the identity matrix or a multiple of it. Okay, so doing kind of the transpose map shows you that this is diffeomorphic to the Stiefel manifold of orthonormal D frames or orthonormal collections of D vectors in n-dimensional complex space. Okay, if I take a quotient by UD acting on by left multiplication, or I guess by right multiplication on the Stiefel manifold, I get what's called the Grassmannian. So this is the set of D planes in complex n-dimensional space, and that is an example of a flag manifold. Okay, so this is more generally true, and I get other types of flag manifolds if I specify other types of spectra. Okay, on the other hand, the other thing I liked to prescribe was the norms of the frame vectors, which was the diagonal of the Gram matrix. So if I pick some reasonable diagonal entries, so let's assume that the norms are all positive, then I'll use parentheses R to say I'm going to fix the diagonal of the Gram matrix to be R. Okay, which is to say I'm just fixing the norms of the frame vectors according to this list. This is easier to see that it's kind of a well-known manifold, right? Because if I take a frame and I say, okay, I want the first vector to be to have norm R1, then that's just saying I want to draw F from a sphere of radius R1, right? And if I'm drawing these independently, there's no kind of global condition like prescribed spectrum, then I'm just really picking each of these from a sphere of a certain radius. Okay, so and because of the full rank condition overall, this becomes an open submanifold of just a product of spheres. So some other kind of familiar type of manifold. And then finally, I could do both, right? And say, I'm going to prescribe the spectrum and the norms of the vectors, which is to say, just take the intersection of these two manifolds. And then things become even more complicated. The resulting thing is not diffeomorphic to any super standard sort of manifold that I know of, and it could even not be a manifold. There's potentially singularities in this thing. So it's some sort of complicated variety. But the general goal of the talk, after all this, is to understand the geometry and or topology of these type of complicated frame spaces. And so, okay, so these are interesting sort of geometric objects in their own right, but what we really want is to kind of make conclusions that are relevant to frame theorists coming from these kind of geometrical and topological facts about these spaces. And I'll mention that this kind of geometric perspective, thinking about these manifolds of frames, goes back. We weren't the first to do this, at least to work with Mixon and Strawn. Our kind of contribution is to use other kind of geometric structures, in particular symplectic structures. Okay, so to tell you the type of results that you can get using this geometric perspective, I'll give you a couple of important geometric results from frame theory, and then tell you how our perspective can kind of tell you something different about these things. So there's a theorem of Cahill, Mixon, and Strawn, which says that the space of unit norm type frames in D by n-dimensional matrix space is path connected. Okay, so this actually, the Larson's REU came up before I started talking, and I think that the conjecture that this is true goes all the way back to that REU, and then this was proved much more recently, around 2017, I think this was published. And this result was a big inspiration for kind of looking at things from a symplectic perspective. And then kind of a more analytical looking result is due to Benedetto and Fickus. So they were studying and introduced this thing called the frame potential. Okay, so this is take frames where all the vectors are unit vectors. Okay, so some open subset of a product of spheres. And consider the function which takes a frame, a unit norm frame, and returns the squared norm of the frame operator with respect to the Frobenius norm set. Okay, and then they show that you have this kind of Welch type lower bound, and that you get equality if and only if F is a type frame. Okay, so here I'm in the space of all unit norm frames, and then you can imagine trying to do something like gradient descent according to this frame potential, and trying to take your unit norm frame and send it to a type frame. Okay, and that one of their main results in this paper is that that approach actually works. Okay, so if you pick, kind of an arbitrary frame and then run gradient descent on it, an arbitrary frame with unit norm for each frame vector, and then run gradient descent according to this frame potential, you will not get stuck in bad local minimums. Okay, you'll always descend to a global minimum. All right, so these are two well-known results in frame theory, and then the kind of the theme of this talk is how to use geometric techniques to say generalize or refine these type of results. So first, I'll talk about a theorem with Clayton Shonkwiler, which says that if I pick any spectrum and any vector of norms, then this complicated frame space is always path connected. Which is kind of like secretly including the case that this could be empty. Okay, so there are certain conditions that these need to satisfy for this to actually have anything in it, but well, the empty set's path connected, fine. So so this is always path connected. And
are you always only considering the complex case?
Yes. So in this row is considering the complex case for reasons that will become apparent in a couple of slides.
Thanks.
Yeah. So this generalizes, at least in the complex case. Yeah, and of course I should mention that the Cahill, Mixon, and Strawn result also considers frames in R D by N, okay, which is harder, and our symplectic techniques at least don't really work in the real case. But yeah, so the proof here uses symplectic geometry, and kind of the idea is that using this kind of high level differential geometry perspective, the proof becomes easier in some sense, depending on how much like weird geometric facts you're willing to swallow. And then we also, together with Dustin Mixon and Clay and Soledad-VR, we kind of refined this Benedetto and Fickus results and showed that if I initialize gradient descent for the frame potential at a full spark frame, then the descent will always converge to a tight frame. Which in particular, the full spark frames, okay, so what are those actually? So a frame is full spark, right? So a frame is like F1, F2, Fn. If I pick D of those, right? So remember this is in D by n-dimensional space. If I pick D of those, okay, then I want that to be spanning still, okay? And so if any D columns that I pick are spanning, I say the frame is full spark. These are dense in this space of unit norm frames. So if I initialize at one of those, then gradient descent, I'll always head to a tight frame. This actually kind of implies the real case here. But yeah.
Tom, can I ask you?
Of course,
Can I ask you real quick, what space are you optimizing in when you do gradient descent?
In this product of spheres, basically.
Okay, cool. Thank you.
Again, so the proof here uses something called geometric invariant theory, which is some subfield of algebraic geometry, but it's closely related to the symplectic perspective as well. And so I'll try to explain that. And okay, the fusion frames are in the title of the talk, I guess. So then a punchline is that actually the proofs that allow us to have these more general results for classical frames, the proofs basically go through in the fusion frame setting. So my plan is I'll try to give you an idea of what these symplectic and GIT techniques are, how they apply to frames, and how those techniques also generalize to proofs for fusion frames. Okay, so we'll start with symplectic geometry. So what is that? So symplectic geometry considers even-dimensional manifolds endowed with an extra geometric structure called a symplectic form or symplectic structure. This is a closed, non-degenerate two-form. What does that mean? So this means, okay, so I'm sitting on this manifold M. And then I pick a point on M. I look at the tangent space. Okay. Then the symplectic structure at that point, okay, so at each point I get a little omega sub x, and this eats a pair of tangent vectors and returns a real number, okay? Now this has certain linear algebra properties, okay, so it should be bilinear, that sounds good. It should be non-degenerate. So if omega uv is 0 for all v, then u has to be 0. Okay, sounds good. Skew symmetric. One way to say it is if I plug in the same vector twice, I get 0. I can combine that. That's equivalent to saying that if I switch the order of my arguments, I pick up a minus sign. So, hence the skew symmetric. All right, so those are all fine, right? So on each tangent space, I have these, very natural kind of linear algebra conditions. Then there's a global, more topological condition, which is to say that the two-form is closed. So there's a notion of taking a derivative of a two-form, and I want the derivative of that two-form to be 0. This is kind of like in the background for what I'm going to say for the rest of the talk, and we won't ever really refer to this property explicitly again. But if you want some kind of intuition, this is sort of like in Calc 3 when you say that I have a divergence-free vector field or something. It's of that nature. It's kind of a more global topological condition. Okay, so let's look at some examples. So one example is I take d-dimensional complex space. I take the standard Hermitian inner product, and then I take negative the imaginary product. So if I took the real part of that, then that's a very familiar thing. That's just like kind of a standard inner product on R to the 2D. Okay, taking negative imaginary part seems also pretty natural. And if I'm in, say, R2 equals C, what is that? It's saying, I plug in two vectors and I take negative imaginary part of their Hermitian inner product. What does that end up doing? It's like the signed area of this parallelogram. Okay, so that's kind of the idea of what a symplectic form is doing. It's kind of eating a pair of tangent vectors, returning a signed area in some sense. And in fact, locally, that's what every symplectic manifold looks like. So this is Darboux theorem, this very foundational theorem in symplectic geometry, says that basically every symplectic manifold looks like this. Okay, locally at least. So that there's a local neighborhood where it's symplectomorphic, like equivalent in the symplectic category to this kind of standard example. Which is quite different from the Riemannian picture, right? So in the Riemannian setting where you have inner products on each tangent space, you have local invariants, which tell you that I can study properties at a point of each of these Riemannian spaces and tell that they are like different in some sense. So I have curvature. There's no notion of curvature really in the symplectic category. And that's mostly due to this d omega equals 0 condition, which is somehow like a flatness condition for symplectic forms. Okay, but just to give you some more examples, frame space. All right, so we're tying this back to frames. We said that frame space is an open subset or an open submanifold of this vector space, which of course is equivalent to C to the D times N, say, so that I can pull back, the standard symplectic structure from there, and I get a symplectic structure on frame space. A kind of compact example is S2 with signed area. So I'm always imagining this as my example of a symplectic manifold. Okay, so S2, the compact manifold, pick a point in its tangent space. It's, still literally like take the signed area of the parallelogram spanned by two vectors. That gives me a symplectic form. And this has this closedness condition as well. And then the final example, which takes a bit more to explain, but which is really important for what we're going to discuss, is coadjoint orbits of Lie groups. So we'll come back to this. All right, so an important aspect of symplectic geometry that kind of makes it interesting, this frame theory perspective, is its interaction with Lie group actions. Okay, so if I have a Lie group acting on a symplectic manifold smoothly, sometimes such an action will have something called a momentum map. Okay, so this is a function from the manifold to the dual of the Lie algebra of G, satisfying two conditions. The first is that it's equivariant with respect to the coadjoint action. So I'm not going to say too many details of what this is. We'll come back to it in a couple slides. But basically, there's an action of G on little g star. Okay, and I want it to be the case that if I act on a point X by an element of my Lie group and then do the momentum map, that's the same as do momentum map, then act by G, in the target space. And then I also want the momentum map to satisfy this differential equation, which kind of basically it's showing you how the symplectic form interacts with the momentum map. Okay, and you kind of figure out where all the moving pieces can possibly go, and then this differential equation pops out. So in particular, if I have something in my Lie algebra, I get an induced vector field, right, by saying, okay, I can multiply something in my Lie algebra by T, I can exp out, I get something in my Lie group, I can act on X by that element of the Lie group, then I take the derivative at 0. Okay, and that's my vector at that point. Right, so on one hand, I can evaluate the symplectic form on an induced infinitesimal vector field and some other vector. On the other hand, I could take the derivative of mu at X, apply it to V, Okay, so then the resulting thing lives in the tangent space of G star, which is just G star. So then I can apply that to an element of G and I get a real number, and then I want these things to be the same. And so momentum maps don't always exist for any given Lie group action. If one does, it's called a Hamiltonian action. And I think I always have this example in mind to kind of get an intuition for what's going on. So if I take S2 with its standard symplectic form, okay, I can act by S1 by rotating around the z-axis, right? The dual of the Lie algebra of S1 is isomorphic to R. And I'm really going to think of that as kind of a vertical line over here. If you work out what this differential equation is telling you, you'll see that it's satisfied by this map, which just takes a point to its height on the z-axis. Okay, so that satisfies these properties. You have to be careful with your identifications and stuff, but this is something you can really work out by hand. Now, intuitively, what's this telling us? It's telling us that I stick a point here, and then the orbit of the S1 action is like rotating around like this, of course. That is constant height, right? So the intuition is that momentum maps pick out conserved quantities of your Lie group action. Okay, and that's just intuitively how I'm kind of always thinking of momentum maps. And that's really why it's called momentum. This all comes from classical mechanics. And so momentum and yeah, go ahead.
Tom, do you know if it's a complete invariant?
Complete invariant, meaning that any conserved quantity is captured by the momentum map?
Yes.
I kind of doubt that, although I can't necessarily 100% answer that right now.
Got it. Thanks.
Yeah. Okay, so we have these manifolds endowed with these extrageometric structures. These things interact with Lie group actions in interesting ways. Then the question is, okay, fine, that's all like very nice mathematically. Why do we care for this particular application? Okay, what does this have to do with frame theory? And in particular, the type of results where you're actually kind of like gaining some insight into frame theory type stuff. So I'll give you a couple like fake theorems. So I'll call them informal, meaning that I'm not really stating them precisely, but these are kind of like conceptually true at least. And we'll hopefully hint at why you might care about these things. Okay, so the first theorem of Atiyah or Kirwan, depending on how you actually turn this into a precisely stated theorem, says that level sets of momentum maps are connected. Okay, so the key thing to point out here is connected. So this is the kind of tool that we use to do our kind of generalized version of the frame homotopy theorem. Okay, so because momentum maps are so highly structured, they have kind of nice Morse theoretic properties, and from that you can kind of discern topological things about level sets. And then secondly, that this is like way informal because I'm not even kind of really saying anything, but if I take the norm squared, so I put a norm on G star, this vector space, and then consider the map, which is like mu, and then take norm squared of that. So Kirwan studied these types of maps really extensively and showed that they have good properties. Okay, and I'll pin that down a little bit better later. But the point is kind of this was the inspiration for being able to kind of say something about the frame potential. Okay, so the punchline is that the frame potential is a norm squared over a momentum map, which means that you can kind of unpack all the stuff that Kirwan knows about these things in this special circumstance and pin down some really kind of precise behaviors of gradient descent there. Okay, so I promised that I would talk more about co-adjoint orbits, and especially because this will be super relevant to kind of actually showing how to prove frame homotopy type results. I'll be, a little bit vague and not give all the details of this just for the sake of time, but let's suppose that we have a Lie group, G with Lie algebra, little g. So there's an action of G on G star, the dual of the Lie algebra. And I won't say what it is in general, but I'll give you an example in a second. But for every element of my group, I get a map from G star to G star. And this is called the co-adjoint action. Okay, add star G. So here's an example, and this is kind of the one we really need. Let's suppose that our group is unitary group, big unitary group with big N. Then the Lie algebra is skew Hermitian matrices. Frequently, when we're doing this stuff, it's useful to like kind of find a bunch of isomorphisms to make things easier to write down. So it turns out that we would prefer to work with Hermitian matrices rather than skew Hermitian matrices. Okay, so multiply by I, say. But then what's more, if I, of course, this is just a general thing. If I pick an inner product on the Lie algebra, then I can identify the Lie algebra with the dual of the Lie algebra. And in particular, let's use kind of the obvious choice of an inner product here. That gives me an identification, kind of combining these two things of Hermitian matrices with the dual of the Lie algebra. Okay. And whatever, it's given by this formula, I guess, but you can kind of ignore that. The point is I have a very precise pin down identification of these two things. Okay, so add star was not really defined and kind of mysterious up here. In these kind of matrix Lie group cases, it's typically very easy to write down. So add star under my various identifications, I can think of as a map from Hermitians to Hermitians. And what does it do? So I have a unitary matrix A. I do add star A of X. It's just conjugate. Okay, so simple enough. So what is a coadjoint orbit? Of course, it's an orbit of the coadjoint action. Okay, so if I take something in little g star in the dual of the Lie algebra, I say, okay, where does it go under all possible adjoint actions? That's what I'll call the coadjoint orbit. So this is denoted O sub C. Okay, so here's really kind of an important example. Going back to the unitary case, so my group is unitaries, my Lie algebra is skew Hermitian matrices. I'm identifying dual of the Lie algebra with Hermitians. And let's assume that D is less than N. Okay, so given a spectrum looking thing, okay, so a lambda where they're written in decreasing order and they're all strictly positive. First, I'm going to pad that out, okay, with, so here I had D things, I want N things overall, so I have N minus D zeros padded. Okay, so I can think of this as something in R to the N. Then I can take the diagonal matrix associated with that and look at its coadjoint orbit. And I'm just going to kind of shorten that and call this O sub lambda tilde. But really, I mean coadjoint orbit in Hermitians of this diagonal matrix. Okay, well, that should be conjugations of that diagonal matrix by all possible unitaries. And then you can show through basic linear algebra that this is, in the end, the same thing as the space of frames with prescribed spectrum lambda, the one that I started with. Except it's up to UD. Okay, so I can only pin down this equivalence up to UD orbits, where UD is acting on the space of frames by left multiplication. Okay, so the punchline here is that, well, this is the first punchline, is that this matrix space this frame space of frames with prescribed spectra, or a prescribed spectrum lambda, mod UD is a coadjoint orbit. Okay, then the fact that makes this especially interesting is that coadjoint orbits are kind of a standard example of a symplectic manifold. So any coadjoint orbit has a natural symplectic form. It even has a special name. Okay, so the Kirillov constant Suryaw form. So this works completely generally. You can always define a symplectic form on these coadjoint orbits. So then in particular, these frame spaces are symplectic. Okay, so then from that, we are able to now combine this with this notion of a Hamiltonian group action and prove this connectivity results fairly painlessly. Okay, so I have a maximal torus, U1 to the n, sitting in this unitary group. The unitary group, of course, acts on its coadjoint orbit. So then that means that the subtorus also acts here. I'm hiding a technical detail here, so read that if you want, but otherwise ignore it. But yeah, so I have this torus action on this coadjoint orbit, which is diffeomorphic to this frame space that I care about. Lie group actions sometimes interact nicely with symplectic structures, and in fact, this torus action is Hamiltonian. If I work out what the differential equation tells me, it tells me that and really what's the kind of the conserved quantity of this? It tells me that the momentum map really is just record the diagonals of the matrix, right? So I take a matrix from this coadjoint orbit. My map is list off the diagonal entries. Okay, so I said kind of a fake theorem earlier about connected level sets. Here's an actual theorem. The level sets of a momentum map of a torus action on a compact symplectic manifold are always connected. Okay, so that's the thing that's actually true. All right, so now I have a frame space that I care about. This is a compact manifold. I have a torus action on it, which is Hamiltonian. I can take level sets. Well, taking a level set amounts to prescribing the norms of the vectors in my frame. So then this is what I just said, and then this proves this connectivity result with some extra argumentation, right? So there's like a couple sneaky things, like really this is true for this kind of quotient manifold. So then if I want to boost back up to the total space, I have to do a little bit of work, but basically this does it for us. Okay, and then so in the original paper where we proved this wasn't kind of the main way that we were thinking of it, but then kind of refining our thoughts a little bit, we realized that you can kind of see a lot of this stuff from the perspective of coadjoint orbits, and that lends itself really well to what are called fusion frames. And so now I want to kind of jump into that and say, how do I generalize these ideas to the fusion frame setting? Okay, so a fusion frame for CD is a generalization of a frame. So and there are different ways you might define this, so I'll go with this sort of definition. So I'm going to think of it as a collection of orthogonal projections from CD to CD, such that the frame operator, which is just kind of the sum of the projections, is invertible. Okay, and then I'll say that if you, in complete analogy with the classical frame case, I'll say a frame is tight if this frame operator is some multiple of the identity. Okay, and then now I want to specify some special frame spaces, so or fusion frame spaces. So now I'll pick kind of a collection of what you should think of as ranks. Okay, so I'll pick a vector of ranks. And I'm going to prescribe that the ranks of my orthogonal projections are given by this vector. Okay, so these are the dimensions of the subspaces I'm projecting onto. Then I'll let FF for fusion frame, super D vector K denote the collection of fusion frames with those prescribed ranks. And then same as in the kind of classical frame setting, then you can say, if I have an element of this frame space, and it's tight, then I know exactly what the constant in front of the frame operator must be. Okay, so it should be the sum of the ranks divided by D. Okay, so this generalizes the notion of classical frames. If I take all my projections to be rank 1, I'm just projecting onto a bunch of lines. If I take unit vectors representing each line, then that's giving me a unit norm frame. Okay, so I want to think of this as kind of a generalization of the elements of this are generalizations of unit norm frames, and also the two notions of tightness correspond. Okay, so then the generalized frame homotopy conjecture or question you might ask is, okay, so I have this analog of unit norm frame space. I could ask, is the subset of tight fusion frames path connected? And then the answer is yes. Okay, so the space of tight fusion frames is always path connected. Once again, there's a little bit of sneakiness, right? This could be empty. Okay, this could be empty. There could be no tight fusion frames depending on your parameter D and vector K. But the empty set's path connected, so I think I'm not lying here. So this collection of tight fusion frames with that type of data is always path connected. Now, depending on whether you buy that this kind of symplectic perspective is natural, the proof is like very painless. Okay, so once you kind of internalize the coadjoint orbit perspective in the classical case, this is really more or less just a straightforward generalization of that. Okay, so I can consider these kind of vectors where lambda j has kj ones and then padded out by zeros. This space of fusion frames with prescribed ranks, I can identify with the space of tuples of Hermitian matrices with these spectra. Okay, and then by the same kind of linear algebra arguments from before, you know, if I take one of these with a prescribed, the space of kind of one of these Hermitians with prescribed spectrum, that's going to be a coadjoint orbit. These are basically independent of each other, so this whole space is a product of coadjoint orbits. Now, if I have a bunch of symplectic manifolds and then I take their product, there's kind of an obvious way to put a symplectic structure on that product, and so you can do so, and then you see that this frame space has a natural symplectic structure. The unitary group still acts diagonally, so it acts on each of these coadjoint orbits, so then it acts diagonally just by hitting each one by the same matrix. That action is Hamiltonian. And its momentum map is take one of these guys, send it to its frame operator, and then momentum maps are well defined up to adding kind of a central element in the Lie group, so something that's fixed by the coadjoint action. So I'm just going to subtract this off for convenience. The point being, what goes to zero? Well, it's exactly the tight fusion frames. Okay, so then here's a real theorem of Kirwan. So this is a generalization of Atiyah's theorem, which says that to get connected level sets of momentum maps, you don't need to take a torus action. This works for more general compact Lie groups. Okay, so even though this is not a torus acting, we still get a connected level set type result due to Kirwan. And then that proves the theorem, basically. Right, so I'm taking the level set of this momentum map in this coadjoint orbit is exactly the tight fusion frames, and then by Kirwan's result, that's connected. And so really, this is kind of a special case of the real theorem in this paper. So we prove something in a lot more generality, that we get a connectivity result for operator valued frames with prescribed spectral data. And then, so this is one example of that. Okay, and so let me spend the last few minutes and talk more about this kind of more analytical results on understanding the energy landscape of the frame potential. So remember, the frame potential takes a unit norm frame, sends it to squared norm of its frame operator. One of Benedetto and Fickus's kind of main theorems in their paper is that the frame potential has no spurious local minima, meaning I can basically gradient descend and never get stuck in a local minimum. And then together with Dustin and Clay and Soledad, we show that if I initialize gradient descent at a full spark frame, I'll converge to a tight frame. So this is using ideas from geometric invariant theory. I guess a thing you might observe, and this is kind of like more of a high level perspective, is that we're all experts on symplectic geometry now, and we know that the map which takes F to its frame operator is a momentum map for a UD action. Okay, so we didn't actually mentioned this at any point before, but you can imagine this is kind of a nice action on frame space, and it in fact is a Hamiltonian action, and its momentum map is take frame operator. So the frame potential is actually the squared norm of a momentum map. I mentioned earlier that Kirwan really studied these extensively and really understood the gradient descent behavior of these functions, and showed that these are kind of these generalized Morse-Bott functions with pretty precise characterizations of critical sets and things like this. So our proof of this theorem was kind of unpacking what Kirwan was doing, and really the way that she was studying this was to find connections between symplectic geometry and geometric invariant theory from algebraic geometry. Okay, so let me sketch the proof strategy at least. So the general strategy is, I think, pretty generally applicable. We find a property, some mystery property of a frame, such that full spark frames have that property. If I do gradient descent on something with that property, the property is preserved, and it's preserved into the limit. And non-minimizing critical point does not have that property. Okay, so if I can find such a property, then that kind of really tells me exactly what goes on in the gradient descent process for this functional. So we weren't using really any heavy machinery from geometric invariant theory, but we were inspired by some concepts there. So if I have a reductive group acting linearly on a complex vector space, think like GL and acting on n-dimensional complex space, or SLN, then I say that a vector is semi-stable for that action if 0 is not in the closure of its orbit. Okay, so the idea for defining a property with kind of the desired features is to work in this kind of GIT setting. So here we take SLD acting on c to the d tensored n times, and it's kind of defined on these kind of basic vectors in the obvious way, and then we can extend linearly. Then our property here with the desired properties, or the desired features, I should say, is a frame F has property P if I can tensor its columns together and it's semi-stable under this group action in the sense of classical GIT theory. Okay, so then the trick is showing that this property actually satisfies these requirements. And that's, of course, the technical part of this. The main kind of machinery we use from GIT is the Hilbert-Mumford criterion, which basically gives you a way to check for semi-stability by checking kind of one parameter subgroups. I mean, that's exactly what it says. So if I take a non-zero vector, it's not semi-stable if and only if there is a one parameter subgroup, i.e. a homomorphism of C star into G, such that the limit of phi t acting on V as t goes to 0 is 0. So that's, a condition which is quite convenient for, checking semi-stability or non-semi-stability. And that basically allows us to show that this property has these requirements, and then the proof goes through. Okay, so I don't want to go too much over time, so I'll just mention how does this apply to fusion frame theory. So Kazatsa and Fickus generalized the frame potential to the fusion frame potential, and it's kind of the same thing. Take the frame operator and take its norm squared, and then they also had a Welch type lower bound on that. And then Clay and I showed that, so here's kind of one version of the results, those easiest to state. So if this frame space has tight fusion frames in it, then all the local minima of the fusion frame potential are global. Okay, and the proof follows a very similar strategy to the kind of classical frame theory proof that I just described a little bit. Basically, you have to cook up a new property that captures semi-stability. And it's this more complicated thing that we don't really have to stare at for too long, but there's some sort of more complicated property that a fusion frame must satisfy. And this relates to semi-stability for the SLD action. Now the trick is you have to kind of do a Plücker coordinate. So you take these wedges of CDs together and then tensor the results. So it's more or less like a beefed up version of the proof strategy in the classical frame case. Okay. Okay. And yeah, let me kind of wrap it up here, but there are many open questions, specifically related to what I described today. You notice that we can characterize gradient descent when I know that fusion frames or tight fusion frames exist in this fusion frame space. And that, classifying the parameters when that happens is a difficult problem. But of course, you can define fusion frame potential no matter what. And what does gradient descent look like in that case? And so I mentioned this, but didn't really describe it in any detail, but some of this stuff generalizes to operator valued frames. The obvious question is, can we characterize gradient descent in these more general operator valued frame spaces? And then the big question is really, these norm squareds and moment maps, you can get a lot of mileage for understanding energy landscapes from kind of knowing that that's the type of function you're dealing with. Now there's a lot of moving parts here, right? It's like a group acting on a symplectic manifold, that has to be somewhere to get the ball rolling. But are there other norm squareds and moment maps kind of that exist naturally, which would be interesting from a kind of energy landscape analysis perspective? Okay, so let me end there. So this is funded by NSF, and here are some references to the papers. Okay, so let me stop there. Thanks, everybody.
All right. Let's first of all stop the recording.